Dirac-von Neumann axioms. You should think of these as the nearest approximation to, say, Newton's laws, Newton's 3 laws of motion, which axiomatize Newtonian mechanics, or the Maxwell equations, or whatever it is you're using to add. These are the things that are supposed to play that role, according to the textbooks. So this is going to be called textbook or orthodox quantum theory. Now, why do I say Dirac and von Neumann? Dirac formulated these in a textbook in 1930, von Neumann in 1932. 1930, that was Principles of Quantum Mechanics. Dirac was in his 20s. Well, let that sink in. He was like 25. Von Neumann, it's 1932 in Mathematical Foundations of Quantum Mechanics, although it was a German title, and it's like Mathematic Grundlagen der Quantum Mechanics, something like that. Okay. They formulated these axioms then, and here are the axioms. This is what the axioms say, and I want you to pay attention to what they say and what they do not say. So axiom 1. Axiom 1 is about things called quantum states. A system's quantum state is a positive, semi-definite unit trace, which means it's trace class, operator or matrix on a Hilbert space of some dimension n, possibly infinite.
That's crazy.
That's axiom 1. Okay. Now, if the quantum state, which is denoted by the Greek letter rho, is rank 1, then it can be factorized as an outer product of the form rho hat equals psi dagger. Although we don't usually write it like this. We write it using Dirac's notation. Psi, where this funny frame symbol is called a ket, and this funny frame symbol is called a bra. You may wonder why he used these funny words, because if you put them the other way, they make a bracket. Apparently, according to The Strangest Man, a biography of Paul Dirac, written by Graham Farmiloe, I highly recommend everything he's written. He's fantastic. His books are amazing. Shortly after this, Dirac was in a dinner with a bunch of very serious University of Cambridge dons who were all talking about various things. And Dirac, who was very odd and rarely spoke, suddenly said, "I invented the bra," and then said nothing more. What the heck are these things? Okay, this is a vector. You can think of it as a column vector. We'll talk a little bit about matrices and column vectors for those of you who don't know about it. It's a column vector. And the dagger just means that we take the column vector and we turn it on its side and complex conjugate all the entries. So this dagger symbol, also known as the adjoint symbol, just means complex conjugate and transpose. So what this is really saying is we're expressing this thing as a row vector multiplied by a column vector that is the same vector, except that we have complex conjugated all of the entries. This is wrote the other way. I always do this. Column vector first. Okay. Column vector multiplied by row vector. Thank you. Now, we'll review matrix multiplication in a moment, but what this gives you is a matrix, an n by n matrix. This column vector here is n by 1. This row vector here is 1 by n, and you multiply an n by 1 by a 1 by n, you get an n by n, which is what this thing is. This thing is n by n, where n is the dimension of the Hilbert space. When this is possible, when this thing is rank 1 and it is factorizable in this way, we can peel off psi and peel off psi, which is just this column vector. I'll just write it out as psi 1 dot 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 psi I dot 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 through psi n. It's a column vector. And this thing is known as the state vector, or through a slight abuse of terminology, the wave function. There's your starring player, the protagonist of the story, the wave function. Make sense? It's clear. I mean, you know, I don't need to say anymore. I mean, it's like obvious now how things work. Okay. Axiom 2.
Right.
Axiom 2 is about unitary time evolution. And it is the statement that if the system is undisturbed by other systems, and undisturbed is a little complicated to define. Somebody would argue this is a bit circular, but for our purposes, we'll say undisturbed means not engaged in mutual interactions, whatever that means, or exchange of information.
Almost, you might say, inertial.
Yeah, so if you begin to worry, this has ambiguity, isn't it, like inertial reference frames? Excellent. But somehow we can imagine a system, it's just left to itself in some way. Okay, but of course, systems in an external, like electric or gravitational field, that's also allowed. So, but that's like quite isolated. Anyway, so you can run all these sorts of questions. But if you're not touching the system, you're not measuring, you're not disturbing it, you're keeping it pretty shielded from its environment, we say the system is undisturbed. If it's undisturbed, then there exists an operator, U, little hat for operators, we use hats for operators, that depends on t is the time, such that rho, the quantum state at any given time, is given by U times rho at the initial time 0 times U dagger. Okay? And this is not just any operator, this operator is unitary, which is a fancy way of saying that if you take this operator, give it as a matrix, and dagger it, you get the multiplicative inverse matrix. It's the multiplicative inverse matrix. So you give me the quantum state as represented by this thing. I should have given it a name. This thing, by the way, has a name. It's called the density operator. Quantum state in general is called the density operator of the system. You give me the density operator at the initial time 0, you wrap it up in U and U dagger, and out comes rho at t. And this is how you evolve the thing forward in time. It's called unitary evolution. Now, if the system has a rank 1 density matrix, its quantum state is rank 1, it simplifies. We only have to worry about the state vector or wave function. And we can think of the state vector or wave function. So if rho is rank 1, which literally just means it can be factorized in this way, well, then the state vector exists. It is a function of time, and you can express it by taking the state vector at the initial time, multiplying it by this operator U, and it gives you the state vector at later times. So this thing that has a name, by the way. It's called the time evolution operator. Now, time evolution operator is a function of t. U hat is a function of the time t if it is strongly continuous, which is a bit of a term of art. Just think of it as smooth. I wouldn't have to the time to define what I mean by strongly continuous. But if it's like very smooth as a function of time, then we could take its derivative. Its derivative exists. We could imagine doing the derivative d by dt of u. And if we want, we can multiply it by u dagger. The resulting object has some properties that are made a little better if we multiply by the imaginary unit, and h bar is just good for units. This thing defines an operator called h. And this operator h by construction is self-adjoint. Its adjoint doesn't change it. The I is actually crucial for this. If you do the I inducement integration by parts, you'll find it the same. And this operator has a name. It's called the Hamiltonian. We say it is the generator of time evolution. And with the Hamiltonian in this equation, you can easily show that the state vector obeys a certain differential equation with a rather famous name and origin story. All you do is take a derivative. You do d dt multiplied by h bar of psi of t. You insert your formula u of t psi of 0 from our equation before, and you can show that this is equal to h hat times psi of t. And this differential equation, which you can think of as an infinitesimal differential version of unitary evolution, is called the Schrodinger equation. And some people have said this is like the dynamical law. It's like the F equals ma of quantum mechanics. Although, as we see, it's actually kind of a special case. You have to assume some things to get this particular equation out. It's not as general as you would have thought. That's axiom 2. Now, axioms 1 and 2 are sometimes called the Hilbert space axioms. And as you can see, they are just math at this point. I have said nothing about physics. I just said that there are these mathematical things, and the mathematical things have properties. Density matrix is positive semi-definite, unit trace, there's a state vector, there's the, you introduce a notion of time evolution, but what does that even mean? I'm just considering a sequence of quantum states represented either by density matrices or more simply when possible by state vectors. But what does this have to do with the real world, the physical world? Well, axioms 1 and 2 don't tell us that. They're just math. And so at this point, you might be wondering, gosh, I haven't seen any quantum mechanics before, or I saw quantum mechanics. This doesn't look anything like what I saw. Where's the particle in a well, and where's the eigenvalues and all that stuff? That's going to come in just a moment. If you're wondering, I don't really understand any of this. Maybe there's something wrong with my brain. The answer is no, your brain is fine. Well, it might not be fine, but not because of this. If this all seems very abstract, that's okay. If you don't understand what's going on and you're wondering, gosh, the person sitting next to me probably understands all this, Let's just next to Stephen. Okay, so axiom 3. Now we're going to connect things up with the real world somehow. Every so-called observable, it's the term that we use, every observable, everything you might want to ask. And observables could be things like position, momentum, energy, angular momentum. There's a whole list of things it could be. Every observable corresponds to a self-adjoint. This can be generalized, by the way, to positive operator value measures we're going to talk about. It can be associated to a self-adjoint operator or matrix. Think of it again as an n by n. So the density matrix is an n by n matrix. A. Self-adjoint means that the thing is equal to its adjoint. If you imagine transpose and complex conjugate, doesn't change it. This is a very special feature. It means this thing has a complete set of eigenvectors and eigenvalues. You may not remember what eigenvalues are, but we'll talk a little bit about that. To this thing, there is associated a list or so-called spectrum. The terms eigenvalue, eigenvector, and spectrum were introduced by David Hilbert, whose name is attached to these Hilbert spaces. David Hilbert. of what are called eigenvalues. And these are real numbers. It's a list of real numbers. I'll call these numbers lambda 1, lambda 2, dot, dot, dot. There are at most n of these. At least, and at most n distinct ones of these. Given that we're in a Hilbert space of dimension n. If you have an observable with more than n, you need a bigger Hilbert space for it. These numbers are associated with this thing in what sense? In the sense that for some vector, I'll call that vector lambda sub a, when your operator acts on that vector by matrix multiplication, what comes out is the number itself times that vector. Actually, I usually draw these vectors without lambdas. I start with this. Label the vectors by the label A. What comes out is that number out front. When a matrix multiplies a column vector, you can get any. Just totally scrambles it up. But if A is an eigenvector, it's a very special kind of vector. When the operator acts on it, you don't get just anything. You get the vector back again, the same exact vector with a number out front. And that number out front is called an eigenvalue. And a self-adjoint operator has this unique, distinct list of eigenvalues that come out. I can give you an equation that tells you how they're uniquely determined by it. This list of numbers are called the eigenvalues. And what does axiom 3 say? It says the possible results of an observer measuring the observable represented by A are its eigenvalues. So if you wondered, if you took a linear algebra class, what about eigenvalues, and they're just sort of like floating around the back of your head, when am I ever going to need these? They're rather important. The self-adjoint operator has a full list of these, and to say that we're representing an observable by one of these is to say that if you go out and measure energy or whatever it is you're measuring, what you can get numerically in your measurement is one of these numbers and only these numbers. These are the numbers you can get. When people talk about what are the energy levels of the hydrogen atom, you measure the energy, that's represented by a self-adjoint operator, turns out to be the Hamiltonian, as it turns out. And the possible energy levels for the hydrogen atom, it's various negative 13.6 electron volts times 1 over n squared, when is the principal quantum number. That list of numbers, those are the eigenvalues of the Hamiltonian. At least most of them. Well, the discrete ones. There's also continuous ones, scattering, but whatever. So this finally connects up these abstract Hilbert spaces with things you can go out and measure. Notice I haven't said anything about the quantum state yet. This is a statement about the possibilities of measuring a given observable. They correspond to the eigenvalue spectrum of a particular operator. Axiom 4, and we're almost done. There are only 5. We're making great progress. Axiom 4 says the probability with which a measurement by an observer of an observable A, probability with which a measurement by an observer of observable A yields an eigenvalue lambda A is given by the Born rule. That's the Born rule, named after Max Born, grandfather of Olivia Newton-John. But no one who's under 40 has any idea what I'm talking about. Is there anyone under 40 who knows what I mean by that? Wow. Born rule. What are the lesser known Jason Bourne movies? What is the Born rule? It says that probability, the probability, that's P probability, with which you will obtain the result lambda A is given by, take the system's quantum state represented by the density matrix, you multiply by a certain operator, P hat, subscript A. What is that operator? It is the operator that projects onto the eigenspace for that eigenvalue lambda A. So we imagine you've got an eigenvector corresponds to A. There could be more than one, but all have the same lambda A eigenvalue. Those vectors span a little subspace of the Hilbert space. And this is an operator that just takes whatever your thing is and projects it down onto that subspace. And then you take the trace. Trace of a product of matrices is the sum of the diagonal entries. Multiply these two matrices together, we get an n by n, and we just sum the diagonal entries. And this is called the Born rule. It roughly resembles, if you just sort of take your glasses off and kind of squint a little bit, it kind of looks a little bit like we're summing, that's the trace, over a certain projected set of probabilities to get a net probability. It's what it's supposed to sort of evoke. Now, this is not the most well-known version of the Born rule. If the projector happens to be rank 1, then it is simply an outer product of this form. It is also an outer product if rank 1. And if the quantum state itself is also rank 1 and is expressible as an outer product as well, if they're both rank 1, then this formula simplifies further. And it just looks like you take the inner product, this is the bracket of A with psi, and you take the modulus and you square it. And it turns out this formula is just what this formula reduces to. And this says we get probabilities for measurement outcomes in quantum mechanics. We take our quantum state, we take the eigenvector associated with the eigenvalue of the probability that the eigenvalue of the observable that we're measuring. We take their inner product, so row vector times column vector gives you a number. The number is in general a complex number. We mod square it, that means we take its absolute value as a complex number and we square that, and the result is the probability. And this rule in its most primordial form was written down in 1926 by Max Born. And the story behind this was Max Born originally did not include the absolute value squaring. And then after the paper had gone through peer review and was ready to be published, he had second thoughts, and so he requested a modification which became a footnote. Note added in proof on further reflection. It is not this, but the modification that is the actual probability. That correction, 1926, won him the Nobel Prize in the early 1950s. It was a Nobel Prize winning correction. Note added in proof. Okay. This is the Born rule, and this gives us our probabilities. We now have probabilities. We can now say what is the probability with which we'll get a certain result. And then as soon as you have done that measurement and gotten that result, one final thing happens, and this is the famous collapse of the wave function, the collapse of the quantum state. That is axiom 5. Because you might say, well, what if I do a measurement and get a result? What if I measure the same thing again? Do I get another probability again? That's not, the answer is, well, you should get the same result again. How is that ensured in quantum mechanics? And this is the final axiom 5. On getting the results, the measurement results, be very clear, use my very clear language here, measurement results, lambda A, the new quantum state is obtained by collapsing the old quantum state down to that eigenspace and normalizing back to 1. For a state vector, what this means is if it's a state vector, you're supposed to replace it with, you act with the projection on that state vector and divide by the norm of the new state vector. We replace the old state vector with a new one, a collapsed one. So for example, if that projector happens to be rank 1, if there's a unique eigenvector, and what this means is that your old state vector is replaced with the eigenvector. And this guarantees if you redo the exact same measurement right away before you allow any Schrodinger unitary evolution, with probability essentially 1, you get exactly the same answer. We lock in the answer. Those are the axioms. I've now given them to you. You now know all of quantum mechanics, all of it. It's now in your brains. You know it all. Okay, now you may have some questions. First question is, what the hell's going on? What about, like waves and stuff? Aren't there like waves flying around and double split and there's like waves that go through the holes? And what about atoms? They can be like in 2 places at once, right? I mean, and chemistry, right? What do they always tell you about the atom in chemistry? If someone says, well, what are the electrons doing in an atom? What are they doing in an atom? What do people always say?
Cloud, they always
It's a cloud, there's cloud. There's an electron cloud. It's like a cloud everywhere. Do you see any clouds here? What's the clouds?
Cats.
Hey, cats. What about cats? See cats here? I see cats. Close. Cats, pretty close. There's cat. Cat.
We got a cat.
What about, you read popular books and stuff. There's like, the particle experiments. They have an electron flies by and it emits a photon, and the photon's emitted. But where is? I don't see any paths of things and photons and electrons. I'm gonna let you in on a secret. All that is just for color.